Yeah, just before we dive into the lecture, two things. You got your assignment number 3. That'll be the last assignment to do. That one is to implement a top-down parser without the look ahead. So you will just need to see how the backtracking can be implemented. So that will be something you can actually dive into. But I would like to just point out certain things you can pay attention to. So if you go to, for example, I already loaded up the projects for your assignment number 3. If you look at AST node over here, of course, you're going to fill out the details. But if you look at ... I'm not sure if you guys have seen this before in Java. It's something called variable arguments. It's actually quite a useful notation. So hopefully you guys can have fun. I'll give you one example quickly. That's a very useful thing to see. Very useful to really build a tree on the fly. You don't really have to build intermediate variables to really build a tree. I'll show you some example. That'll be one thing you want to pay more attention to. So let me show you one example here. So if you look at one of the starter tests, for example, here you can see we got some root over here. And then this entire thing is a giant expression to build a binary tree, or well, actually a general B tree. So here I say AST node, we're just building some abstract syntax tree, basically. And can you imagine what kind of tree is being built over here, right? In order, I'm going to show you some example here, but before that, what makes this possible is because in general for AST, you can have as many child nodes as you like. So at the time of declaring the method for AST constructor, you don't necessarily know how many children you might have. One way to do it will just be have an array over here. But using ... is actually much more convenient, so you guys can play around with that. That's actually quite a cool feature. So here, if you say ... that means you can pass one or more child nodes over there. If you look at here, for example, let's look at this. This one here, we have some root, which will start with just expression. Okay, so that means we got expression over here. And then how many child nodes do we have? You can see we got one here, we got one here, only 2. So that means under the expression, we got turn and also expression prime. Let me just do one more and you'll get the idea. Under the turn, how many child nodes do we have? 1 and also 2. So we got factor and also we got turn prime. That's how you build a tree. And at the same time, you can see how many child nodes are under expression prime. 1 here, and 1 here, 3. So it's not really a fixed number. So the ... is a really cool notation for you to get used to. All right, that's something I thought you might just want to know before you start tackling assignment number 2. Are we okay with this? That's the only thing I want to mention to you. Other than that, I think you just need to spend some time debugging your top-down parsing method. But you can definitely refer to the slide where we got a pseudocode. I think that one got more than 90% of what you need. But there will be certain Java details you have to figure out, which is fun. That will be the purpose for the assignment. All right, that's for assignment number, actually here I put 2. I really meant 3. And for your milestone 2, I just found that E-class is now being slow again in delivering my announcement. Okay? And I would say we follow this basically the same pattern as last time. I sent out 2 announcements to you guys, actually just one. Earlier this morning is about the project milestone 2 meeting. Okay? Basically, I'm just giving the same time on Wednesday and Thursday. You guys can sign up. And it will be tomorrow, Wednesday, 6 p.m. The link will be available. Just in case, 6 p.m., you don't really receive an email announcement. Just log into E-class. I'm pretty sure it will be there. Okay? Sometimes email delivery is pretty slow. And then your milestone number 2 deliverables, items will be also due to next Tuesday, November 22nd, okay, 11:59 p.m. I'll release a PDF just detailing what you have to submit, like last time. 2%, not really much. It's just for me to check your progress. Okay, as long as it's not too ridiculous, you haven't done anything, it should be fine. We'll leave the more rigorous grading maybe in the final submission. But for now, just to give you feedback. Okay. Okay. Have you guys got any questions so far? Project? You okay, right? Okay. I presume you guys are fine. And for today, I just want to cover 2 things quickly. One would be about the algorithm for calculating the first set. I'll recap very briefly about why we might need a first set. First of all, number one. Number two, we'll go over the algorithm and go over some example. And number three, we'll actually do some extended first set computation. Rather than reading a single variable to calculate its first set, can we read a sequence of variables for calculating the first set? That's a very nice, very straightforward extension. That's all we need to cover today. And then on Thursday, we'll move on to the so-called backtrack-free parsing algorithm. That's what we'll do. And then hopefully next week, we can talk about bottom-up parsing, which will be another flavor to do parsing. Okay, so let's now move on to the slides. And that's the slide that we went over last time. Basically, this slide here just tells you that there is such a notion called the look-ahead symbol. This is something we would like to use in order to save us some time for doing backtracking. In order for you not to do backtracking, you ought to know if I choose this particular rule for derivation, am I really going to hit that symbol to match the current word? If I can, of course, I'll go for that. If I cannot, I'll just simply wouldn't build a subtree, right? I want to really avoid backtracking. That's basically what we said last time, just remember. And we talk about the first set. If you recall this little page over here that we did last time, right? So this idea would be, if I want, let's say, now currently I got expression here. If I want to choose this particular rule, for example, in that way, what will be the very first symbol, terminal, I will actually see? And we actually got some intuitive calculation last time. It's pretty much what the algorithm will do. So that's why we don't need to spend too much time today. But I'll show you the algorithm and also show to you the pattern matching part you have to watch out for. And everything else will be up to you. Okay, let's now, first of all, go over some definition for the first set. So here, I don't need to go over. That's basically from your project description about Milestone 2. Nothing has changed, but I'll make it more concrete when I release the PDF, most likely tomorrow or by Thursday's class. Okay, so that will be the algorithm for the first set. Let's try to look at these two together. Okay, let's focus on this one first. This is more like an abstract definition for the first set. Okay, the alpha here. Okay, let's take a look. Whenever you want to do a computation for the first, you can pass on alpha. Alpha can either be a terminal, like a symbol, or it could be a variable. There are two cases. In the case where the alpha is simply a terminal, what will be the first set for terminal? What do you see first in a terminal? Well, just the terminal itself. So that's why it's simply just alpha. That's very straightforward. You can think about that's the base case. What about the recursive case? If you actually got some variable over here, basically what you need is to somehow go through some derivation step. Right? You can see that exactly over here. In order for me to figure out the first of certain variable, it's going to be all the words. So you can think about the W here, all the terminals, or the words. That's why you see W is simply sigma star, right? There's no variable here. All such W, alpha is able to be derived into something starting with W. And the beta over here is something we don't care. Okay? You can think about W is the starting symbols. And such string can be derived from this alpha, which we want to calculate its first set. Okay, that's the definition. And yep, that's the abstract definition. That's something you can maybe spend a little bit more time looking into once we have gone through the algorithm. Any part of the definition you are not so sure about, you want me to go over. But I think that's pretty much it. Okay, just remember, the W over here should be all terminals. That's something you will see. Okay, but how do we calculate this? Algorithmic, using an algorithm. How do we do that? Okay, let's take a look. So this is the algorithm over here. Okay, it's simply just called get first. The input will be a context-free grammar with variables, terminals, rules, and also stop variable. And you can see T here is simply just a terminal. That's fine. What will be the output? And this is something I want to emphasize. The first over here, you can think about the first. Remember this symbol over here that actually we spoke about, maybe back in the DFA or NFA formulation. It is a function, right? Just remember. Or think of it more like a hash table, like a hash map. What will be the key? The key for the map will just be either a variable or a terminal, or simply epsilon or EOF. So these are the possibility as the key. Whenever you pass anything as the key that's valid, it's going to return back to you a set of terminals as the first words. That's a computation. Okay? So the way to read this would be, so the first. So you can think about given a valid terminal or non-terminal, return its first symbols, leading symbols if you want to think of it. Okay? And let's now go over this algorithm quickly. It's actually not that complicated. You just need to understand mainly just about the for loops over here, which I'll definitely give you some intuition. It's mainly here, but we'll get there. Before that, let's take a look at the initial stage. For this part over here, this is just building up the base cases. The first for terminal. If you remember back in the definition, for any alpha that is a terminal, the first will just be a singleton set, just the terminal itself, right? That's what we're doing. For all the alpha that is a member of the terminal, EOF or epsilon, the first of alpha will just be the alpha itself as a singleton set. That was easy. And then initially for all the variables, we just let its first to be just empty. We don't have anything just yet. Okay? And then this part over here is a little bit similar to one of the algorithms that we did previously. I'll tell you what it is. Remember how we compute the lazy evaluation for the DFA, right? Converting from NFA into DFA. We said that the while loop itself is looking for some fixed point. As soon as you get to a point that you cannot really make any further new discovery, in that case, you stop the loop. Similar over here. So what you can think about is, as soon as we reach a point that the first map cannot be grown or updated any further, that means it's now time to stop. So we don't really go indefinitely. Okay? That's really important to also observe. You can think about, as soon as the first map cannot be grown, and then you exit from the loop. Okay, that's kind of the inside. But let's take a look what you're supposed to do. When you actually calculate it, let's go over quickly and we'll do one example. The main pattern to see is like here. We say for each production rule that has this kind of form, you can think about the first component is called beta 1, and second component beta 2, all the way to beta k. Okay? That's how we start with. And then we're actually going to collect some information from beta 1 for sure, but we only get to beta 2 if somehow beta 1 is nullable. Do you remember the notion about nullable before, right? Okay, intuitively, let me show to you. Intuitively, if I know, okay, let's take a look here. That's exactly here. Let's say this is the layout for A. Beta 1 over here, we want to think about what is beta 1. If the epsilon is a member of the first of beta 1. Okay, this is case number 1. And we also got case number 2. It is not a member. Okay, let me write it down and I'll explain. Epsilon, not a member of first of beta 1. We got two cases over here. And let's pause a little bit to think about it. Case number 1 and case number 2. What would be one example of case number 1? I'll show you the grammar here. If you look at term prime produces epsilon, that means it is possible when you actually want to use this rule, the first one you see is actually an epsilon. That makes no contribution to the ultimate string, just epsilon. That'll be case number 1. Case number 2 would be when epsilon is not in the first. That'll be one example. One example would be, let's say this one here, factor. You can see in order for me to choose the factor, I can see the first character either being the opening parenthesis or some number or some name. There's no epsilon over here. So this is kind of the case where we can see the symbol right away. There'll be no need to go any further to beta 2, beta 3, and then beta k. Okay? Right, let me write some annotation here, and then we can move on to the algorithm. So for case number 1, when epsilon is there, so that means need to move on to beta 2, right? We want to look at beta 2, and the same pattern will go on. Beta 2, there are also 2 cases. Either beta 2 has epsilon in its first set, or beta 2 does not have it, right? Follow the same pattern. You will see that exactly in the algorithm, which I'll show to you. And for case number 2, when epsilon is not there, that means stop right here. No need to go to beta 2. So after I have gone through the example with you in the next page, you can definitely review about these 2 cases. For every component over here, you just want to see if beta 1 is nullable. In that case, I might have to collect beta 2 as well. If beta 2 is also nullable, I may need to look at beta 3. Another scenario, if beta 1 is nullable, of course I look at beta 2. But let's say beta 2 itself is not nullable. In that case, we don't really need to look at beta 3. We just stop there. That's why you will see there is a loop over here. I'll help you a little bit to gain some intuition from this loop. Can somebody tell me, based on the for loop declaration here, under what circumstances do we actually exit from the loop? Precisely. A Boolean condition. What Boolean condition should we? Of course, you will need to look at this middle part here, right? But this condition here tells you under what circumstances you have to stay in the loop. To exit from the loop, it needs to be its negation, right? Exit when either the epsilon is not in the first of the current one we're looking at, or we are reaching the end, I larger than or equal to k. Right? This Boolean condition here actually is very important, especially the first one. The first one over here, when we say epsilon is not in the first of the current component beta I, that means we should stop here. Don't really try to collect the first components from any later components. And that's exactly case number 2 that we talk about over here. So when you study the algorithm, try to link this exit condition here to case number 2. All right? And here we say as long as we actually got more beta I that's nullable, we can keep collecting it until we hit the wall with something that is not nullable. Okay. Let me put it here. Keep collecting. The first until is not nullable. All right, and finally, the final condition here is what I highlighted here, and then look at this one here. This one is to say if the loop counter here is exactly equal to k, and remember we only got k components, that means we have now reached the end of the components for this variable a, and everything is nullable. What does that mean? That means a itself is also nullable. If a is nullable, then epsilon must be in its first set. Okay? So here that means every component, okay, every component of A is nullable. That means A is nullable. In that case, we should really include the epsilon into its first set. Right, it's a very quick walkthrough about what the algorithm is supposed to do. And then we're going to do example. All right? All right, spend some time with the algorithm after class with yourself, and then come back to me if you got any trouble. Okay? Let's now look at one example. Okay, so how are you supposed to trace? We wouldn't trace completely, but I'll just give you some idea. Okay? So here is some principle. You should really choose, let's say we are given this grammar here, so that's the input. And the output should be, you can think about the first is more like a map. So you can, these are the keys of the map. It can be some terminal over here, and these are the variables. And the value should be the corresponding first symbols for the terminal or non-terminal. That will be the output. And the principle will be, you want to choose the rules in certain order. I would say the order is really arbitrary. It's kind of up to you, okay? But for me, I'm gonna cheat a little bit. I want to choose this particular order, just easier for us to see. In case you got this question on the quiz or the exam, you can choose any order you like to really do the first set calculation. Because as long as you don't really reach the fixed point, you should really keep going until you cannot really go any further. All right? So that's a grammar, which we looked at last time very briefly. Okay? Let's now take a look. Let's do the simple part. This part over here, simply just build a base case. For every one of the terminal and also EOF and epsilon, the first set will just be itself. So for none, it will just contain none. For name, it will just be name. Plus, minus, multiply, divide, opening, closing, EOF, epsilon. Base case, very easy to build. And then, initially, we're also going to initialize all the first set for the variable 1, 2, 3, 4, 5, all to be just empty to begin with. That's all we're going to do. Okay? And let's now dive into this loop to see what's going to happen. Okay, this loop. Okay? And let's say, let me choose F to be the first. Okay? Factor. If I look at the factor over here, that'll be the first iteration, factor. And then I got the first rule I'm going to check would be factor produces, let's say, you can think about this is more like a beta 1, like a beta 2, and beta 3. Okay, think of that. Okay? This will be a very representative example of what a loop is going to do. And it's a simple case to handle. Given that we got beta 1, beta 2, beta 3. And then, do you guys know if we should do anything over here? It turns out, in this case, let me start with this. Here, what will be the first of beta 1 over here? You can see the beta 1. Let me put it here for the very first iteration. So we got factor produces this, also expression, and also this, right? Let me be more precise. So that's beta 1, beta 2, beta 3. Okay? What would be the first of beta 1? Should be over here. That's how we start with. Okay? And then set difference, the epsilon, you will have no effects because epsilon is not there. And then we're going to run this loop. And for this loop over here, how many iterations are we going to run? Remember the purpose of this loop. It will try to maybe collect, for example, let's say here, beta 1, beta 2, beta 3. If beta 1 happen to be nullable, in which case we have to also collect the first of beta 2. Is this the case? No, it is not, because beta 1 over here is actually not nullable. So we just stop there. So we don't even execute here. It's not executed. Okay, I'll write a note here. So this one here, this part over here is not executed because the first of beta 1 over here does not contain epsilon. It does not. Okay? So that means eventually what's going to happen is we'll simply keep just the first of A. In that case, which just accumulates this symbol over here. It will just be this symbol here. So after the first iteration, we'll simply get, for the factor, we just get this. That's after the first iteration. We just collect that. What about the second rule? Well, the second rule would be we just go for this one here and also this one. Both of these are also not nullable. We just keep growing. All right? So that means after the next iteration, we get this and also the num. And after the next one, we'll get this and the num and also the name. Okay, so this will be the calculation for the first of the factor. So this will match what we actually got intuitively last time. If you look at what we got last time over here. So I would say depends on how the question is being asked. If I just give you the grammar and you just want to figure out the first set, you might just be able to just look at this and see, okay, that's a terminal, collected. That's a terminal, collected. That's a terminal, also collected. That's the intuitive way. But you ought to also understand how the algorithm will also make it work, just over here. Okay? Are we okay with this, just for now? Why don't we do one more? And then I got a little challenge for you that you can think about. How do we compute? Let's see, okay, I gotta watch out the time. How do we compute over here, let's say the E prime. Let me use a different color here, E prime, expression prime. How do we compute the first over here? And there are 3 rules to go over. Rule number 1, rule number 2, and rule number 3. All these, right? What's going to happen is you can see the plus and also minus. So these are terminals, in which case we just collect them without going any further to. You don't really go here. You don't go here. So for the expression prime, first of all, you will get a plus, and then you will get plus and then minus. And the final one is going to be the epsilon. Okay, the epsilon, if you try to trace this code over here, what you just remember, whenever you got epsilon, it would just be collected right away. Because it's only this one here. You don't have any further components to actually collect. You just collect it. Okay? Plus, minus, and epsilon. This input grammar here is rather straightforward. You don't have any special case where you will go beyond beta 1. But I'm going to give you one case where you might have to go beyond beta 1. Okay, I'll give you one case. Okay? Right? If you want to continue, you can continue with the term prime, term, and also expression. The algorithm itself is very straightforward, so you don't need to worry too much. So here's one little exercise for you to think about. Okay? Hypothetically, let's say we want to add this rule to the grammar. So that means for the expression prime, we want to add another alternative. Okay, so you can think about here, or turn prime factor. Okay, that's the change I would like to introduce. Don't worry too much about whether that really makes sense for the ultimate language. But I want you to really look into this to see the following. If I got term prime, for example, we know that term prime is nullable, first of all. And then later on, when we try to execute this line specifically, is it going to run for one iteration or no iteration? It turns out it will actually run for one iteration because given that this is, remember we actually got a pattern, beta 1, beta 2. So you can think about this is beta 1, this is beta 2. In this case, we know epsilon is actually a member of the first of 10 prime. Right? You can see epsilon is over here. So that means when we actually want to collect the first of expression prime, it's going to be, of course, plus, of course, minus, of course, epsilon, and of course, it's going to be the first of 10 prime. It's going to be the plus, the minus, the epsilon, and also the first of 10 prime. And the question is there anything further? Indeed, because since 10 prime over here is nullable, so we should also move forward to look at a factor. So we also need to collect all these as well. Okay, that's the critical point I want to show to you. Also union with the first of factor. All right, that's the main thing to show to you. Okay. So what should you know about the first set? Number one, know its purpose is to avoid backtracking. Number one. Number two, how do you calculate it intuitively, like what we did last time, like over here. And number three, also understand the algorithm, actually how it's calculated mechanically. Right? These are the three things. Any question about the first set? Okay, what we will do on Thursday is to see, in order to really have a backtrack-free parsing algorithm, having just the first set turns out to be insufficient. We need another set called the follow set. That will make things a little bit more complicated, but we'll try to go over that, and then we'll finish the backtrack-free grammar. All right, that'll be the plan. All right, I want to stop here, and then I got your quiz number 2 paper over here. I'll hand it back, and then I'll give you back quiz number 3 on Thursday. Okay, guys, thank you. I'll see you on Thursday.